background to talk about the 360 covering both spaces and why it's called the 360. So,
is that why it's called 360?
yeah. So anyway, so that's what I talk about in terms of core generally, but you can embellish it and talk more or less depending on the audience, how your timing is going, and so on. Then I also talk about people, and the slice of people that I use is typically Seymour Cray. Another option is to talk about Gene Amdahl, and you can stop at the whisk and talk about the whisk, stop at the 360 and talk about his contribution to the 360, and then point out the Amdahl 470 and Gene's participation. And that can also be an opportunity to say a lot of the pioneers of computing are fellows of our museum and are contributors to the museum. And this museum not only operates based on volunteers, but on donations and so on. And so we encourage people to donate their time and material and money and stuff. So that's another option. In the 45 minutes for a basic tour, I find I don't have enough time to talk about both Gene Amdahl and Seymour Cray. And I choose to talk about Seymour Cray just because there's several more places around the museum that we have Cray machines, and there's some really interesting stories about the 6600 that I like to talk about. But I do point out that Seymour Cray, this was the first machine that he was the principal designer for when he worked at Sperry Rand. He left control data after the prototype was built and before they were actually built, but it's his design. This is a tactical computer for the Navy. It was actually out on a ship.
He left UNIVAC.
He left UNIVAC, I'm sorry, before control data. And it was actually sealed up to keep out the salt spray, and it was on a ship keeping track of all of the information they needed and their navigation and so on. But a characteristic of Seymour Cray design that you'll see started here and continued is lots of little small modules. This concept of building blocks, that instead of having large circuit cards that are very specialized and complex, we'll do what I call the Lego approach, is we'll have a fewer number of small circuit cards that we can better stock and so on. And by properly wiring the backplane to interconnect them, I can make the same circuit card behave in different ways and be used for different circuits and computational things. So Seymour went on to Control Data, and Control Data was also struggling with building general purpose computer. And Seymour said, well, I have this great idea that I designed over here, and that was these little building blocks, but they needed to sort of prototype it to confirm that it was okay. And this is the actual prototype that Seymour Cray built himself, called the Little Character, and it's a full computer. It's got a core memory, a console, power supply, but if you look at it, there's maybe 12.5 different kind of circuit cards, but they're just replicated multiple times, and all the complex wiring in the back connects it so that that circuit card might be to control the memory in this place, but the same circuit card over here might be part of the add circuitry. And you could do that with this building block approach. I just read, in fact, last night an interesting story that Seymour was building this, and he kept going to surplus places to buy the parts for this, and he had bought a whole bunch of transistors really cheap, and he went back to buy another batch, and they were like 2 or 3 times more expensive. And he says, well, what gives? It's the same transistor. And they said, well, the ones we sold you before were rejects. They didn't meet all the characteristics, and the manufacturer got rid of them, but these are all good. And it was a tribute to his design that, in fact, some of these transistors that didn't meet operational specs still worked in this machine because of his conservative design of how he operated the machine. So the next stop is halfway down here. And I really like stopping people in this aisle and giving them a feel for what was happening in computers in the 50s and 60s. And what I talk about is that there's sort of 2 sets of development lines going on in computers. Computers historically have been one monolithic mainframe machine, and over time it's gotten bigger and bigger and faster and more capable and more expensive, and it got to the point where on this line of mainframes that are getting better and better but bigger and bigger and more expensive, you got to the point where you never touched the machine. As a programmer, you'd write out your code, someone would key punch it, maybe it's you, but someone would key punch it, feed it in, and a professional operator would run the machine in batches. And the machines were so expensive and so difficult to operate that they had these trained operators running them, and you never even got to see the machine or touch it. And that was great because there's a lot of problems in the world that need a big machine to crunch the numbers. But at the same time, electronics was allowing computers to shrink. and to get smaller. And at the same time as mainframes were getting bigger and faster and more expensive, there was this whole approach that started out with what we now call mini computers, and then got into micros and your personal computers, where computers were getting smaller and smaller. And a real great example of that is the PDP-8 right here that we passed, that's on my right, in the black case right here. So this is what I call the Classic 8. Digital Equipment Corporation was founded specifically to build smaller, cheaper computers that they could have a single computer for a single purpose. That machine in the mid-1960s cost $20,000, and you got the processor, 4K 12-bit word memory, and an ASR 33 teletype as the console and the paper tape reading and punch device, and you could do accounting on that. Or you could run an instrument in a laboratory. And it became cheap enough that companies would invest in buying several computers for these specialized purposes. So at the same time as computers are getting bigger and faster, they're getting smaller and more personal and cheaper. And so that's a $20,000 price point. We'll show you what happened to prices when we go into the next bay of the room. But computers getting bigger and faster kept going on as well. Seymour Cray went to Control Data, where he worked, and said, I have this concept for a machine that would be significantly faster than all the mainframes we have today. And he designed a machine called the 6600, and that's what you see here. This is actually half of it. There's 4 cabinets that make up the 6600. And I should point out this is serial number 1. You can come a little more forward. They were not configured this way. They were normally in an X shape, with all the cabinets, and the electronic portions were together in the center, and all the cooling is on the outside. Seymour Cray said, let's really push the state of the art, and let's really design a computer to be significantly faster. This machine from 1960 to roughly 1965 was the fastest computer we know of in the world, and it could do several million floating point operations a second. Now to do that, the electronics had to operate with pulses that were 1 nanosecond in the nanosecond range. And a nanosecond is a billionth of a second. Well, due to physics, electricity, or actually light, but electricity is close enough, travels only 11.8 inches in a nanosecond. In a billionth of a second, it travels a foot. So you look at this machine, and there's 3 really interesting physical characteristics you can notice about the machine. First is, in addition to the electronics, there's all this plumbing. Well, this machine ran so hot and so fast that traditional cold air, forced air cooling, couldn't keep this machine cool enough. So they literally plumbed these copper pipes in between the circuit cards and pumped Freon through it to pull the heat out of the machine. And if that Freon pump ever failed, if you didn't stop the machine, it could literally melt down. It ran that hot. Second thing you'll notice is if you look at the wiring, it's twisted pair. When you talk about a computer that runs slower, electrical noise isn't as much a problem. But when you get into this speed of computer, electrical noise and the electromagnetic radiations from other parts of the computer can affect, yet other parts of the computer. By using twisted pair wiring, the 2 wires sort of cancel out that electrical noise, and the machine runs more reliably. The third thing, and the thing that I find most fascinating about this machine, is if you really stare at it for a while, you'll notice that there's some short wires in the machine, but there's also a lot of really long wires. And what the heck are they thinking? Why waste all of that wiring in the machine? So here's the problem. No matter how well you organize the circuit elements to be close together that you need to, you're always going to have places where, let's say I have an add circuit, and one input to the add circuit is coming from the circuit board right next to me, and the other input to the add is coming from the cabinet over there, 8 feet away. Well, it's 8 feet away. We're talking about billionths of a second timings. The pulse from over there takes 8 nanoseconds to reach here, but the pulse from the circuit card right next door comes instantaneously. The 2 pulses do not arrive at the same time. So what do you do about it? Well, the classic way that we've solved this in computers, and most computers before then and even after this machine, do it by adding another little circuit in that add circuit that's a latch or a memory. and it remembers the first pulse, and then when the second pulse comes, it can combine them. But that means more components, more size, more cost, less reliability, more heat, more electricity. Seymour Cray's brilliant idea was, I can't make the signal over here, 8 feet away, get here any faster. That's the closest I can get the circuit. But I can sure slow down the signal from the card next door. If I make this signal go through the same 8 feet of wire that this signal does, then they'll both arrive at the same time. By making the wire longer and slowing down one signal, they both arrive at the same time, and the machine actually runs faster because you can eliminate this latch circuit. So he slowed down the machine to be able to speed it up. And it's just such a simple concept, but no one had thought of it before Seymour Cray, and it allowed him to eliminate a lot of the components in his machine to make his machine smaller, faster, cheaper, more reliable, and ultimately it ran faster because he slowed it down. I've had school kids through here that I've given that same talk to, and they can walk around here and find every Seymour Cray supercomputer in the room because it has these twisted pair and the long short wires. It's just really remarkable that he did that. The other remarkable thing is this was the fastest computer still in 1965 when it was replaced by a successor, the 7600, which ran about 4 times faster. And it was one of the first times where a manufacturer replaced a machine that wasn't yet even obsolete with something even better to sort of keep ahead of that curve. But it too uses Freon cooling, the twisted pair wires, and the short long wires. It's a typical classic Seymour Cray design. And this again is serial number 1 out of Lawrence Livermore Labs.
It looks like it's all there now.
Well, we got 2 of the quadrants. I think there were 3 or 4 quadrants altogether. I don't remember the configuration. So I don't have time today because we're doing other things, but I like stopping in this corner and I point out 2 things. One is I point out the Cypress, the photo-digital store, and I talk about how this could store 1 trillion bits of data. It was used at the Lawrence Livermore Labs, and it's all done photographically. There's literally in these trays little cartridges. In the cartridges are little pieces of film stock, and the machine literally pulls out a film strip, runs it over to the other cabinet through a pneumatic tube mechanism. A high-powered light beam records a pattern of 1s and 0s on the film stock, feeds it through this chemical photo developing lab, like you'd have 1-hour Photoshop, dries it off, puts it back in the cabinet, and then reads it back out again later and can read the pattern of 1s and 0s. And the interesting thing about this machine is I use this as an opportunity to talk about, as a history museum, we want to collect things that were not only significant in history and successful, but things that were failures or things that were moderately successful. They only made a few of these. By some ways of thinking, this was not a successful product, but it met the needs of the customer, and we learned a lot from it, and some of the things we do today were because of things we learned from this. There was one IBM service engineer responsible for this machine at Lawrence Livermore Labs, and when he decided it was time to retire, they had to retire the machine because no one else could maintain it. He was an expert in photo, optics, electricity, mechanical things, software programming, the chemistry of the developer and so on. He had to tweak this machine and keep it running and putting a shim here and adjusting that. And he was such an expert at it that they literally had to retire the machine at the point that he wanted to retire. But it served its purpose. They stored several trillion bits of information over its lifetime with all of this data from nuclear experiments and so on. The other thing I point out in this corner is the 3, and I normally elaborate a lot more than I'm giving you guys. I talk about the 360, and I talk about this as a real important point in computing history. Prior to the early 60s, the situation was every computer was unique. Every computer was incompatible with every other computer. Even though IBM built several computers, some small, some large, they weren't compatible with each other. And so let's say I owned an IBM computer and I outgrew it. I needed something bigger or faster. And I go back to IBM and I say, I need a bigger computer. They said, not a problem. Okay, here's the next bigger computer. And it only costs you this much and it's so much faster. And it's so... But unfortunately, it's not compatible, so you have to rewrite your programs. Now, high-level languages like Fortran and COBOL were starting to come into being, so that made the problem a little bit easier, but you still substantially had to reinvest in redoing the software, if not totally throwing it out. It was not compatible. Imagine you have a home PC and you go down to Fry's to buy the new faster one, and they tell you, great, we'll sell you the new faster one, but you know that $1,000 you spent on buying software? You have to throw it out and buy all new software. I mean, we just wouldn't stand for it, but that was the situation in the 60s, until a machine like the 360. And the concept here was that they had a common instruction set architecture that they designed, and then they built little bitty machines that could run those programs with that instruction set that had slower times, less memory, less capabilities, and big machines that could run the same software but faster. And then you as an IBM customer would invest in all your software development on a 360-30 like this one, and when you outgrew it, you could go buy the next bigger 360. And IBM was very happy to swap the machines for you because they kept you as an IBM customer, because all of their machines were software compatible. Today, we just come to expect it. Back in the 60s, that was a revolutionary idea. So I try and really enforce that with people and use that analogy with the home PC about, you know, upgrading from a Pentium 2 to a Pentium 3 and throwing out your software.
Do you talk about multiplexer channels and
Nope.
Standard interfaces?
Nope. But if I have the right group, I do.
Yeah.
You know, I talk about that standardization. I talk about how this was a single machine that handled both business and scientific,
Right.
which is why they called it a 360, because it handled the whole, and it sort of replaced the notion of a 1401 for business and a 1620. I'll talk about the peripheral industry and how IBM had been leasing their machines and then were forced by lawsuits to also sell the machines, and that people were building clone peripherals. And I'll point out the Data Products printer up there. That's serial number 1, model 1 of a clone printer that plugs into a 360. And so, you know, depending on the group, again, that's how you adapt and move things along. But for the general tour, I don't get into that level. I do, as we're walking by, point out that we have some analog computers here, and that when we think about computers, we think about modern digital computers, but analog computers have their place too. There's some problems that you can naturally solve easier with an analog computer than a digital computer. And the example I use is the Norden Bombsight. That this is really an analog computer that figures out if you're going to drop the bomb and the plane is moving at a certain rate and there's winds and everything else, how will that bomb fall? That's a very complex problem to calculate. It would have taken a whole rack of electronics to do it with a digital computer, and they didn't have room on the plane for that. But here in a small analog computer, they could do that. So I relate to analog computers, but it's just sort of in passing as we're moving on. And I always stop here and talk about Hollerith. So here's the problem. The US government, by law, must take a census every 10 years. The 1880 census, once they had collected all the data, took about 7 years to do all the analysis and the processing. And they both wanted to collect more data in the next census, and there were more people. There was a big influx of people coming into the country, and they projected that the 1890 census might take as much as 12 years to process. But they had this little problem, because after 10 years they have to start all over again, and so it was a problem that would never finish. So the US government literally held a contest to find some mechanical, electromechanical device to help automate the census process, particularly the analysis part. And there was a worker at the Census Bureau named Herman Hollerith who proposed the winning scheme. And what you see here is a reproduction. To be honest, truth in advertising, in this museum we have 2 reproductions. Everything else you see is authentic and the genuine thing, but this is a reproduction. But it was built by IBM to the original design specs, so it's a very authentic reproduction. And the notion here is one of using punch cards. Hollerith had this idea that he could represent every person in the United States on a punch card. And you could describe things about that person by where you place the punches. Now, unlike the punch card that most of us were familiar with, Hollerith's card was a little bit wider and a little bit shorter, and instead of having columns of punches, it had zones of punches. But the concept is still basically the same. Where he got the idea was from train conductors. Now, there's a misinformation in the history books that it's sort of the Jacquard loom was his idea. I read his diary, and he got the idea because he lived outside of New York, where he commuted into work every day, and he took the train. And the train conductors would take your ticket and punch it, but they had a secret code where they would punch this corner if you're a man, this corner if you're a woman. They'd punch along this edge proportional to how old you were, and so on. And so they could take a ticket, and they could, by knowing the code, say, this isn't your ticket, this is from about a 20-year-old woman. And so he got the idea that you could describe characteristics of someone by where you place punches on a card. And that was the real insight he had for this equipment. Not the Jacquard loom, but the New York ticket takers on the trains. And the concept, though, is one card per person. You'd go out to the field, collect the data. They would put them in big trays, bring them to processing centers, where an operator would, one by one, put the card in, close down the handle. These spring-loaded pins would go through the holes, connect with a pool of mercury, and tick one of the counters. So you'd clear the counters, you'd run through a whole tray of data for a neighborhood or a county, and then you'd write down the counters and go on. Using this equipment, the 1890 census, once they had collected all the data and it was on punch cards, took about 6 weeks to do the processing and the analysis, compared with 7 years with the 1880 census. So it was very successful. The problem was Hollerith had left the Census Bureau to form a company to make these machines, and because of the pricing and like that, the government leased the machines. So Hollerith did the 1890 census, and the government congratulated him, great success, thank you. Why don't you come back in 10 years when we need to do it again? And he goes, well, what am I going to do with all these machines? So he spent the next several years developing a company that went out and marketed this and variations of this machine to other businesses and other government agencies that could do problems of keeping track of things. He went to the railroads. He went to companies for doing inventory work and so on. And by 1914, he had merged his company with a couple of other companies, and that became IBM. And when he retired in 1924, Tom Watson Sr. was hired to take over IBM. And it was Tom Watson Sr., if you recall, that said for the Johnny Act, no, IBM won't do stored program computing. It wasn't until he retired and his son, Tom Watson Jr., took over that he saw the future in stored program computers, and IBM started building stored program computers. But it sort of started with Herman Hollerith and the punch card.
When did Tom Watson Jr. take over?
I don't know. I don't know. So then I talk about
Late 50s.
what Hollerith did with his company is build a whole assortment of electronic accounting machines that you could literally run your business on. And if you had inventory, you might have one card for every item, and you'd have on it a description of the item, its product code number, the number you have in stock, the price per unit, and you'd have machines that could do simple manipulations of that. They might be able to multiply the two numbers and add them up and tell you the total value of your inventory. Or they could do a comparison of how many you have in stock versus how many minimally you want and print out a list of what you have to reorder. And by using these machines to reproduce cards, sort them in certain orders, run them through printing machines, run them through simple accounting machines to do simple calculations, you could run your business on it. And it sort of harks back to the ENIAC that you changed the machine's operation by rewiring it, but the advantage they had is they had these plug-in boards that you could rewire and just pull the boards in and out of the machine quickly and have a stack of boards, one for accounting, one for payroll, and just swap it in and out. And you didn't have to physically keep rewiring the machine, which was time-consuming. When we got into modern computers in the late 40s, 50s, since all the other businesses were all running on punch cards, and they had punch cards for inventory and payroll, that was the natural input-output device for computers. That's where all your data is. So they hooked these machines up to the computers, and that was the main input-output devices for computers going forward.
We also designed the A-bombs on those things.
Yeah.
Calculated.
Yeah.
Wrote codes with them.
Yeah. It's remarkable what you could really do with some of these
They
machines.
were in great demand in
Yeah.
World War II because they were the only thing you could do a lot of calculations
Right.
that needed to be done.
Right. At my university had a little program for 407 accounting machine that made a raspy sound with the printer and actually made music by printing out a certain combination of numbers. So just remarkable. So I sometimes will mention the mechanical calculators that we have in the collection. This afternoon, when I have the fourth group, I'm definitely going to stop at the 1130, which I normally don't do because that was the first machine that Charles had written, Charles Moore had written fourth for, was the 1130. I might mention the Amdahl if I was talking about Gene Amdahl and the Whisk machine, if I'm talking about clones and the ability to have another vendor make a clone machine that could run the same software. I'll talk about the Amdahl. I typically don't, but that's an option. Come this way. So again, here's a variation. I will sometimes stop and talk about the sieves, Lamer sieve devices, and I will point out that this is the other reproduction in the museum. Again, this and the Hollerith machine are reproductions. Everything else is authentic. But this was used by the famous mathematician D.H. Lamer to do real work, real calculations that he needed to do in his work. And in your binder, there's a whole page on this and the kinds of equations they could solve. But what I usually tell people is, I point out the IMP. And I'll ask people, how many of you are connected to the internet? And you know, almost every hand goes up. And I say, you know how there's a little plug in the back of your computer and you just plug in a wire and you're done? Well, back when the internet started, it was really the ARPANET. It was done by the military. And it took this whole cabinet of electronics to connect between your mainframe computer and this network of other computers to share data. And inside it is a Honeywell mini computer, a 516 computer, and it does all of the protocol stuff to take messages from your mainframe, break it up, send it off to another machine. If it's not there, pass it on to the next, the store and forward stuff, the redundancy, the error handling. TCP/IP protocol was developed for the ARPANET and was the main protocol used by this machine. But just as a sense, this is what it took in terms of physical equipment to connect to the ARPANET. And today we have a little chip on your motherboard and an RJ45 plug in the back, and you have your cable modem, and you're connected to the ARPANET doing it today. You know, technology is just shrinking.
But everybody had one of these locally at their own.
So they had them in key places, and if you had several, this could handle several machines. So there might be one like at Stanford, and if there was a local college that needed, they would be connected to Stanford's IMP. It started out with just 3 nodes between Stanford and UCLA was the Network Measurement Center. And actually one of the early nodes was actually done in a van with packet radio as a transmission media. And we have out in the parking lot that ARPANET van.
Really?
I may also mention that, you know, we talk about wanting to preserve the history of our industry. It's not just the stuff, but it's people's accounts, it's the paperwork, it's the documentation. The person at SRI who was responsible for the early layout of the ARPANET and assigning IP addresses, in fact, she came up with the idea of .com, .net, is one of our main volunteers. And she had the foresight to save all of the paperwork from the early days of the ARPANET. And when she left SRI and they didn't want to keep it, she took it into her garage and paid for a storage place. And we now have that in one of our warehouses. We have a whole room with all the early documentation, paperwork, requests for proposals, and ARPANET maps, and everything from the start of the ARPANET is now part of the permanent collection.
What's her name?
That's Jake Feiner.
What about the map?
So that map, I sometimes will mention that for the date on the map, which I think was early 70s or something, it's
late 70s.
it shows late 70s. It shows the number of nodes, ARPANET nodes, that existed today.
I think this would be more like a DSLAM if you've got a DSL connection. This is on the other end. It's on the net.
Yeah, this is on the net. It's closer to the cable modem.
It's not at your place. It's
the other
that
side.
you connect.
Right. The key thing is it depends on who I'm talking to, how specific I get. If I have people in here who I say TCP/IP and their eyes glaze over, or someone who says, oh yeah, well what about the third layer of the ISO? I will talk about different things. What I'm doing today is sort of what I would do for the normal 1 o'clock, 2 o'clock Saturday tour, and that's enough generalization that's not incorrect factually, but gives them a reference point. And that's what I mean, again, about a soft tour versus a hard tour. So then I walk along here a little bit and I talk about how a lot of people saw Seymour Cray's success with supercomputers and had their own ideas of how to build bigger, faster machines, either by pushing the technology or multiprocessors or like that. And there were a lot of computer companies started to do this high-end computing, the big mainframes, the supercomputer kind of stuff. And for the most part, they're all gone today. And I often refer to this as our graveyard of supercomputers with thinking machines and the KSR-1 and the Convex. And I talk about there was two companies, Alliant and Stellar. They both were having financial problems. They merged and became Stardent, and then that failed. But the important thing here is not that these companies happened and then they failed, but what did we learn from it? You take the example of a company called Sidrome, and one of the things they pioneered in their architecture was a thing called predicate execution. And the new Itanium chip from Intel is based on predicate instructions whose design came from the Sidrome machine. So even though that machine came and went, we don't even recognize it as the name of a computer company anymore. We learned a lot from their failure, and we took the best parts of what they did forward, and we keep seeing it on and on. Seymour Cray left Control Data and formed Cray Research and continued building bigger, faster machines, and their first machine was the Cray 1. But if you look at it, it too is cooled by Freon, short, long wires, twisted pairs, and the machine was so expensive, Seymour believed that computers should be as aesthetic as they are functional, and you could get these panels basically in any color scheme you wanted. His follow-on machine was the Cray 2, and we have the only 8-processor Cray 2 ever built. This machine runs so hot and fast, even Freon couldn't cool it, so it's liquid-cooled. It literally is sealed up, and this inert, electrically inert liquid called fluoriner is pumped through the machine and across all the circuit boards and all the components and wires and everything to pull the heat away from the machine. And actually, if you get a group who is more technical, you go beyond that explanation. I use that explanation as a general thing. The real explanation that's a little more technical is it isn't so much to cool the machine as it is to stabilize its temperature. The key thing is Seymour Cray, because of all this tricks of timing he did, of making signals arrive at the same place at the same time, the performance of the components was absolutely critical. He had to have this transistor switch in a certain length of time, and to do that you had to stabilize its temperature. It didn't necessarily have to be hot or cold, but it had to stay the same temperature so that it would always switch at the same rate. So what they actually did with the fluoriner, it isn't so much that they cooled down the machine, but they pressurized it and they heated up the liquid to the boiling point. And liquid at boiling point is very stable temperature-wise, and that temperature liquid flowing across the components stabilized the components at a particular temperature in a very narrow range, and that allowed them to operate at a continuous level. So it wasn't so much that it was cooling the machine as it was stabilizing the temperature. So you get someone who's more technical, you can talk about that, but the general explanation of saying this is Freon cooled, this was air cooled, this is liquid cooled, that's good enough. You use the term cooled sort of generically, but in fact it's temperature stabilization that they were after.
What was the boiling point? What was the
I
temperature?
don't know. I don't know. But it was certainly hotter than 70 degrees or whatever you try and keep computer rooms at with the cold air. And they could, by controlling the pressurization, they could control that boiling point right to the level they needed it. So then I'll walk around here, talk about some various machines, again depending on the time and interest of the people. I'll say, if you thought cooling the machine with liquid was interesting, here's a company that cooled their machine with liquid nitrogen. And literally, the computer, the main part of the computer is in this vat of liquid nitrogen to keep it cool. But think about the maintenance problems. You want to repair a broken part of that computer, you have to drain off the liquid nitrogen and store that somehow. You must slowly let the components warm up so they don't thermally crack. Repair the part, put it in, slowly cool it down, and refill it with liquid nitrogen. The company was not a business success. But, you know, they tried something new. Sometimes I'll just mention this machine, and I'll talk about how we collect at the museum. We typically are passive at collecting. When people have something, they contact us. We hear about something, we ask for it. We typically don't go out looking for specific things. an exception to that is the IBM 1620. That when we did that project, part of the project was not just to restore the machine, but experiment with proactively going out and finding everything we could. And we were very successful at it. But this is an example of sort of opportunistic collecting. When I took my eldest son off looking at colleges 5 years ago, we went to University of Santa Barbara, and they had this machine in the computer science department in a room with spotlights on it. They very proudly showed it on the tour and mentioned that it was kind of obsolete and they were getting rid of it. And I said, excuse me, I have a place for it. And we worked out an arrangement with the company that built it and Santa Barbara and us that it was donated to us. The problem was the cabinetry, although it looks kind of slick, was built on site. And it's not structurally strong enough to withstand moving. So we have a guy who's our mover. He works for American Airlines, or American Van Lines, North American Van Lines, and he flew down to Santa Barbara to figure out how the heck to safely move this up here. And he literally designed on a cocktail napkin on the airplane an exoskeleton that he could build with pallets and straps and so on to hold the machine together enough to transport it up here. And we now have that paper napkin also in the collection. So, you know, we do opportunistic collecting, but we also do focus collection. And if you know of somebody or some company who has something to donate, we actually have a collections committee, and we ask that you go to the web and you contact the collections committee and describe what you have. Some things we don't collect. You know, we want the first one of these, we don't want the 10th clone. We already have 5 of them. Or it's something that's sort of outside our collection criteria. So the collections committee really decides what it is we want to collect and approves things. And we typically, we do not pay for artifacts. And we typically, if someone wants to get some money for it, we'll get some donor to buy the device and then donate it to the museum. That's how we got the 1130. We actually had a volunteer who cared about that machine and preserving it, and he paid someone who wanted money for it, and he paid the moving expense to move it to us. So that's how we fund things. But as a rule, you know, and this is typical of museums, we don't buy artifacts.
What is this machine? You said it was.
Oh, this is a multi-processor system. It comes in 2 configurations. The original was using SPARC microprocessors and a big array of multiprocessors. And this one, I think, just uses 68,000 chips.
It's a Sun. Oh, okay. It's not
Okay.
a Sun.
No, it's not a Sun. It's a Mako. It was a European company, a British company. Sometimes I'll stop and mention, again, if I have people who are more involved in the electronics of what's going on. If early on I started talking about some of these machines and the electronics, if I see a lot of eyeballs lighting up, or they told me at the beginning of the tour that they're more hardware engineers, I will sometimes stop briefly at the Fairchild symbol machine and mention that this machine is one of a kind. They only built one of them. It's got 2 claims to fame. It works on symbolic logic, not normal Boolean logic. And Fairchild, which was a maker of integrated circuits, needed a way to package the integrated circuits in a very dense way to build this machine. And they literally designed the dual inline chip that we're familiar with for integrated circuits to be able to package the integrated circuits for this machine. So this machine has a very minor blip in the history of computing, but in terms of electronics, this is what drove them to package integrated circuits in this familiar dual inline chip. So it's got an important place in history.
Before they were packaged in round containers? Or?
Yeah. They did all kinds of crazy packaging. So I'll sometimes stop briefly, and when we're running short on time, so we'll go into the next one quickly. I'll sometimes talk about the iliac, and I'll point out some things. If I got a lot of recognition from people about World War II and the Cold War, I'll talk about this and the Vietnam War. How the government had paid the University of Illinois to design a machine that Burroughs manufactured that was going to be housed at the University of Illinois, but this was during the Vietnam War time. The machine was going to be on the ARPANET to be shared, but there was a bombing at the University of Wisconsin as a war protest, a bombing at the physics department. And the government said, oh my God, we can't put this multi-million-dollar semi-secret government machine at an unprotected university. So with just less than a year's notice, this machine showed up here at NASA Ames, and it was given to a bunch of physicists. It wasn't complete. It wasn't operating. They didn't have schematics as to how it was built. It didn't have an operating system or compilers. And over the years, they developed all that to make it useful. And one of the interesting things about this machine is it's a SIMD machine. Single instruction, multiple data. And here's the concept. Let's say I have 1 million numbers I need to add up. That's going to take me a certain length of time. But if I get 9 friends together, I can tear that into 10 pieces and give each of my 9 friends a piece of it. And we can all simultaneously do the same operation, but with different data. We're all adding, but with different numbers. And at the end, we can add together our subtotals. That's the concept here. There were 64 processors, 1 control unit, 1 set of instructions that told every control unit to do the same operation, but on its own set of data. And then they could combine the data at the end. So that was kind of revolutionary. And they did something that we today call blocking algorithms of how to break up a big piece of a problem, do it in pieces, and then splice the pieces back together again. You know, think of predicting the weather. If I could break, you know, the world map into quadrants and have each processor do computation on a quadrant, there's still the interaction between all of the different quadrants with each other. So that problem of how you break it up, do the computation, and splice it back together is very complex. They pioneered some of that work on this machine, and today we take it for granted.
So it's something like parallel processing?
It's multiprocessors, yes. But the unique thing is each of the processors is doing exactly the same thing.
Yeah, it's
Today's it's parallel processing. Today's multiprocessors typically are doing separate things.
It's an array processor rather than a vector processor.
Right. So let's go in the center bay. I want to keep to my 12 o'clock promise. So but sometimes I'll point out the Enigma as we walk by, only because a lot of people have heard about it or seen the PBS specials. I'll sometimes mention the Zusa, which is a German machine from the 1960s. So I'll blast through this quickly and not talk about content as much as just structure of how I give the tour in this area. I always stop at the 1620 and pay homage. And again, one of the things you want to do is personalize the tour. And for me, this is personal. When I was 14 years old, I was in a math science accelerated program, and I had access to a local junior college's 1620. It was the first computer I ever used in my life. And I was privileged to, a few years ago, lead a team of volunteers. Tim was one of them. We spent 2 years every other Saturday, and we restored this machine to full operation. And we did this thing I mentioned about selective acquisitions. That when we started, we didn't have a console typewriter, no peripherals, no software, few manuals, no schematics. And over several years, and in the internet, this was just wonderful using internet and news groups and email and so on, we now have 4 filing cabinets of original punch card software for the machine. We have most of the manuals, all the textbooks on the machine. We found an authentic 1620 console typewriter, and we restored this to operation. And it wasn't just restoring it to operation, and it certainly was an emotional thrill the first time we turned it on and we got to operate it and feed through problems. But it was, you know, how do you run a project with a lot of volunteers over a long period of time? What are the rules for doing a restoration? You know, we can't just plug it in and smoke test it. We can't go down to Radio Shack and buy spare parts. We literally had to disassemble the machine and test it piece by piece and build it up at a time and get it operational. But you look at a machine like the Johnny-Ac that started in one configuration, and in its lifetime it sort of morphed. If you were to restore it, what do you restore? The original configuration, how it was in the middle of its lifetime, how it was at the end of its lifetime? You face the same problems that people who restore automobiles face. Do you restore it to how it looked as it came off the assembly line, or how it looked in real operation? Do we take off all of these stickers and tags, or is that part of the history that we need to preserve? So this was the first restoration effort for this museum in California, and I had written a formal proposal to the museum about doing it, and then we had very careful rules we made up of what we could do and couldn't do. And it was always the case that if we reached a point where we would take the risk of leaving the machine less historic than when we started, if we were to destroy something by what we were doing, we would stop the project. The end wasn't to get it fully restored. It was to learn about how to do restorations along the way. So now we learned and we modified our instructions. Now we have a better set of rules of how to do restorations, and we're looking to do more restorations in the future. One of which might be the PDP-1. That's high on the list to restore. But we want to restore different technologies, some punch card equipment and so on. But we've also learned how do you go about collecting things proactively. I wrote to Lou Gershner while I was still CEO of IBM and said, can we have legal permission to put these manuals on the website? And he said yes. And that's our foot in the door with IBM to get legal permission to put on our cyber museum other IBM documents. We're doing a simulator on the website that's a graphical simulator to reproduce the experience of running the machine. And there's lots of things that we've learned from this project. And that's more of what we want to do, and part of what we need a large volunteer base for, of experience and knowledge and everything else. So besides that, there's robotics in the corner, but I sort of break this room into 3 pieces and talk about it as 3 separate pieces. I point out that this side of the room is what I characterize as East Coast computing, and this side of the room is West Coast computing. And as I said, the museum was started 20 some odd years ago back in Boston by Digital Equipment Corporation, and this is actually part of the original museum. So when you see better signage and displays, that's because this was in a real public museum, and it diagrammed the history of Digital Equipment Corporation, starting with the PDP-1. Now this may not look particularly small, but this is considered to be a mini computer compared with mainframes. This would only cost $120,000 for a basic configuration PDP-1 compared with $7 or $8 million for a mainframe. And an interesting story here is that it's called a PDP-1 because at the time it was built, the government had a restriction on buying computers. Because they were so big and expensive and they cost so much to maintain and program, if you wanted to buy a computer, you had to go through all of these levels of red tape and approval. This machine was so cheap that an organization that had enough budget could just go buy one. But if it was called a computer, they would automatically have to have it approved. So instead of calling it a computer, they called it a Programmed Data Processor, PDP. And they were very original in their naming, PDP-1, PDP-4, PDP-5, PDP-6, PDP-8, and so on. But they came up with that name as a marketing thing so that they could sell to organizations and avoid, if they were government installations, having to go through all the red tape. And as you walk through the exhibits here, the signage is really good and explains a lot. You'll see the progression of these mini computers getting smaller and smaller and smaller. And just like what IBM did with the 360, having a compatible line of machines, big and small, you'll see the same thing in mini computers. A little bit with the 8, but particularly with the 11. There's little bitty 11s and great big 11s that do different levels of processing, but they all run the same instructions. So I don't even walk people through here, even if I have time. I just encourage them to walk through on their own and look at some of the signage. It's really well done. We have some different memory technologies in this cabinet down here, including a Selectron memory that came out of the Johnny-Ac. So that's kind of interesting if you have someone who's interested in memory technologies to point out. Then I mentioned that this is an exhibit that we designed and built, we the museum, under funding from Intel for a computer show. And it represents Silicon Valley's contribution to computing. And so it has things like the audio oscillator that started Hewlett-Packard, the HP 35 calculator that sort of revolutionized carry-it-in-your-pocket calculators. When this came out in 1975 for $400, I bought one. I was a math science major in college using a slide rule, and my mom couldn't believe that I'd spent $400 on this electronic gadget. And I said, Mom, you don't understand. The difference between 2 digits of precision on a slide rule and 10 digits of precision here is just unbelievable. We have in the cabinet, we walk past a little mechanical calculator called the Curta, that several 100,000 of these were made. You have one? No. Okay. I have one in my personal collection. And it was a very successful mechanical calculator, and their business went to zero essentially when this machine came out because it was so much more capable. We have on the other side the engineering prototype for the Palm Pilot. We have Steve Wozniak's Blue Box. We have the Apple I. We have a Sun One, a glass teletype that started Sun Microsystems. We have a Cisco router. But we also have this machine, the Buzzcomb calculator. And this is important because there was this Japanese calculator company who contracted with Intel to develop a set of chips to do a calculator function. And Intel came back to them and said, well, we have a different idea. We would like to build a set of chips that implements a computer. Granted, it's a very small, limited capability computer, but it's a computer nonetheless, and that we program it to operate like a calculator. And Buzzcom said, that sounds great, but we don't want to pay for that extra stuff. And Intel worked a deal where Buzzcom paid for and only had the rights to use this set of chips for calculators, and Intel retained it for everything else. Well, good thing, because in here you'll see the Intel 4004 microprocessor chipset. That they expanded into 8 bits, the 8008, the 8080, that they expanded 186, 286, 386, Pentium, and this whole line of microprocessors from Intel started with this Buzzcom calculator. And again, to talk about the soft history, we had Ted Hoff, who was one of the designers of this machine, at one of our events the museum gives, and he and I got talking, and come to find out, the computer he used at Stanford was the 1620, and part of the design of the 4004 was based on some capabilities of the 1620. So again, it's a very, intertwined history of computing. As we walk through here, we can tell people different stories of things. And then in my last 2 minutes, I'll just point out the wall of micros and workstations. And most people recognize stuff here, and what I try and point out is a couple of key things. One is that back in the 1975-76 time frame, we had hobbyist computers available. You could write to Altair or Southwest Technical or MSI and get a kit that you could assemble yourself, do all the soldering and wiring yourself, and build yourself a personal computer, if you will. It was great for the hobbyist, didn't take off very well in other applications until 1977, when 3 companies, Radio Shack, Commodore, and Apple, came out with pre-assembled, take it out of the box, plug it in, and start running it computers. And that just revolutionized computing. And later on, IBM in the early 80s came out with the PC line of machines, compact. Their first product was a luggable version of the IBM PC. This weighed something like 30, 40 pounds. You had to plug it into the AC, but an accountant could lug it between his different clients and do the computing right on site. And that was really sort of revolutionary. We get into laptops and so on. This is where I divert a little bit and I say my personal opinion of why the Apple was successful in history was because there was these 2 guys at college looking to do a project, a senior project, and they invented what's called the electronic spreadsheet. They took an accountant's physical spreadsheet and they built an electronic version of it called VisiCalc. And they had 3 machines to choose from of which one they were going to program it for. This machine had 16K bytes of memory, 16K bytes of memory, 48K bytes of memory. Well, clearly you need room for the program, but data. The bigger the memory, the bigger the data. So they chose to write VisiCalc for the Apple, for no other reason than it had more memory. And the minute it came out, every business wanted to buy one. They bought an Apple II just to run VisiCalc. And of course, they figured out clever ways to expand the memory beyond 48K. And they could have done the same thing to these 2 machines, but it was too late. This is the one that really took off. The other thing that made them successful is in education. In California, Apple gave one of these away to every public school. Now you need software, you buy software for the computer you have. Now you have all this software and you want to buy a second computer, what are you going to buy? Another Apple. And so by giving the first one away, they just took off like crazy in the educational field. And in my opinion, that's why the Apple was so much more successful than these other 2 machines. It wasn't because technologically it was any better, but because they had made a decision of having more memory available, and VisiCalc was written for this machine, and the fact that through a marketing thing they gave one away, that's what made them successful. So it isn't necessarily the best thing technologically that wins or is successful, but there's a lot of other factors. That's one reason I'm looking forward to the talk Monday night on the venture capitalists, to get their insight as to how do they go about selecting a company and whose products might be successful. It can't just be on a technical basis. So I talk about that, and then I talk about how at Xerox PARC they had been doing a lot of experimenting with other ways of interfacing with a computer. Not just typing commands and seeing text on a screen, but windows and a pointing device called a mouse, and that they had the Alto machine and later the Star that pioneered a lot of this user interface that we come to expect today. Xerox didn't really know how to market that well. Stephen Jobs visited them, saw the prototypes, was inspired and said, that's the way that people can interact with computers. He went back to Apple and they built the Lisa. Not very successful as a product because it cost $10,000, but it was the first machine out of Apple that had a mouse and Windows. Then they followed it up with the Macintosh, and by then they had it right, and they got the cost down, and they became successful with it. But it was based on concepts that came out of Xerox. And so, again, the whole computer history is someone gets an idea, someone else builds on it, another company does something, and it all moves together, and there isn't clear lines of demarcation often in what's going on. So that's where I end the tour, is here. I encourage people to, on your way out, if you didn't sign in when you first came, please sign in. I encourage you to take any of the literature that's there. We have our core quarterly magazine. We have information on our next talks. There's also an evaluation form that I ask you to fill out if you have a moment to say what you thought of the tour, what we could do better or different or so on. And please become involved with the museum. Come to our talks if you're interested. Become a volunteer. You could either be a docent or you could help move equipment. You can help us on the website. We have a lot of needs for volunteers, and if you go to our website, you can find out how you can become involved in preserving and sharing the history of the computer industry with the other people in the Valley. And then I thank people, and that's the end of the tour. That's okay. I'm done. And amazingly, last Saturday,